Why are Ket vectors important in Dirac notation? Imagine trying to describe a quantum system with just words. It would be nearly impossible. Instead, scientists use a special language called Dirac notation. This notation is like a shorthand for the complex world of quantum mechanics. At the heart of this language are Ket vectors, written as psi. These are not just symbols, they are the mathematical way to representing the state of a quantum system. Think of a Ket vector as a detailed snapshot of a particle's condition, like its position or momentum. These vectors live in a space called the Hilbert space, which is a fancy term for a collection of all possible states a quantum system can have. Using Ket vectors makes it easier to do calculations. They allow us to combine states, see how they change, and predict what might happen when we measure the system. For example, a qubit, the basic unit of quantum information, can be in a state 0 or 1 or even a mix of both. These states are represented as vectors, like 1, 0, 4, 0, and 0, 1, 4, 1. When we want to describe a superposition, we just add these vectors together with some coefficients. This is much simpler than trying to describe the same thing with words or pictures. Ket vectors also pair with bra vectors, written as psi. The bra is like the mirror image of the ket, and together they form an inner product, written as phi psi. This inner product gives us a complex number that tells us the probability of transitioning from one state to another. If the number's magnitude is high, it means the transition is more likely. This pairing simplifies the process of calculating measurement outcomes and expectation values, which are the average results we expect when we observe a quantum system. In quantum computing, Ket vectors are the foundation for designing and understanding quantum gates and circuits. Each operation on a qubit is a transformation of its Ket vector. When we measure, the ket collapses onto a basis state, giving us the result. Without Ket vectors, describing and manipulating these states would be much more complicated. So, in simple terms, Ket vectors are important because they give us a clear, consistent way to describe quantum states mathematically. They let us use linear algebra to understand superpositions, evolutions, and measurements. They work hand in hand with bra vectors to tell us the probabilities of different outcomes. And they are the core language for building quantum computers and understanding quantum phenomena. That is why Ket vectors are a key part of Dirac notation and the foundation of quantum mechanics.